Okay, so the last thing we're going to talk about is the memoryless property of the exponential distribution. And the idea here is that we understand that regardless of sort of what happens in this Poisson process or this anything that's sort of governed by the exponential distribution, which can be a lot of things, it doesn't matter what happened up until a particular point in time, as long as you're sort of going forward. It has a memoryless property. It's sort of synonymous. I mean, it's the continuous version of the geometric distribution, where regardless of how many heads that you flipped up to a certain point, it really doesn't matter because it the next on the next flip you still have a 50-50 shot. So you could have flipped 10 times in a row ahead, but it doesn't matter because the next flip is also ahead. So that's the point of this distribution. It's the continuous version of that. And so let's just let me make sure that I have I have my little red thing here. And so this is what we're talking about just for a couple minutes, so you understand. So in this scenario, what we have is I want to find the time until the next event. So that's going to be my random variable. And we have event N occurred. And then I want to know, so this amount of time, oops, I'm trying to figure out, well, what's the probability that the next event occurs within that amount of time. So we're going to say that's x is exponential alpha. And then if I were trying to find that, it would be the probability that x is greater than or equal to t. Remember those rules of probability where I can flip it one minus, where I can flip the greater than, make it less than, and we can do this and find out that it's just e to the negative alpha t. So what we'll say next is that we have a little bit more information. So let's just add a little bit more information to this little timeline here. And let's say that we know for a fact that it hasn't occurred by t naught, but we're still interested in that same amount of time. So whatever this distance is, I'll just add a little bit and say this is t plus t naught. So now what I'm saying is I know it hasn't occurred up to this point, and the question is, what's the probability that it still takes a t amount of time in order for it to occur, right? So if that's the case, then these are my probability statements. So I'll start way over here because we're gonna write a lot of these out. So I know the random variable x we know is greater than t. Or, I'm sorry, this is what we're trying to find the probability for, but we know it has to be greater than t naught already, right? So that's the new piece of information that we're given. So conditional probability, everyone hopefully remembers how to work with that. It's just the intersection. So the random variable x is greater than or equal to the intersection of these two. So t plus t naught intersect x is greater than or equal to t naught, right? So we know we're past that when the next event occurs. All divided by, if you remember from your probability class, that it's just divided by that guy. X is greater than or equal to t naught. So we know that's what we're trying to find. I want the probability of this. The neat thing here is that, of course, the intersection of these two, right? So the intersection of these two is going to be, so it's got to be greater than t naught, and it's got to be greater than t plus t naught. Well, we can just know that, this part basically goes away, and it's just the intersection of those two is just x has to be greater than or equal to t plus t naught, all divided by the probability that x is greater than or equal to t naught. Okay, so now we're sitting in a situation we can start substituting in our CDFs. So this would be 1 minus the CDF. So this would be 1 minus, and it's going to look weird, I guess, 1 minus e to the negative, is that alpha t plus t naught, right? So all I did was I put this into where x goes in your CDF, and then all that divided by a 1 minus e to the, and then this goes into where the x goes, so it's negative alpha t naught. All right, so again, simplifying this, the 1 minus 1 obviously goes away, and the negative comes in and makes that a positive, and then I can break this up into two pieces. I'm going to break it up into e to the negative alpha t times e to the negative alpha t naught. So take a second and just multiply those two and just see that it's the same thing as as this piece right here, right? So it's the same as just this guy, because that's what happened. That's what's left over after we do the minus and negative and whatnot. And then we all divide it by this thing, which is the only thing that's left over down here. So it's e to the negative alpha t naught. And then these things all get canceled. So I actually shouldn't say these things all, just this one and this one gets canceled. And the fortunate thing for us, because this is a memoryless property, that it really doesn't matter, e to the negative alpha t. It doesn't matter that we knew this new information, as long as the amount of time in between t naught and t plus t naught remains the same, you still get the same probability. Just like flipping a coin gives you the same probability regardless of how many times it's occurred. So don't get caught in that. If you ever try to go to a casino and see that red occurs 10 times in a row, well, black must be coming up soon. You still have the same probability of it occurring, and that's where the casinos get a lot of gamblers. Okay, because they don't really understand the memoryless property. Okay, well, that's all I got for this video. Hopefully you guys got something out of this one, and we will see you next time.